Hello, my name is Juliet Carpet and I worked with Cameron Russ and we did our project on using composites for joint replacements. We are primarily focusing on knee and hip replacements. Joints need to be replaced in order to relieve pain and restore function after either trauma or disease. This is a very prevalent issue since there are thousands of joint replacements a year, and sometimes the joints need to be replaced after time and wear. Some of the time, cartilage from the body can be used, but sometimes the joint is replaced with a man-made implant. The goal for making man-made implants is to reduce the wear due to the amount of friction between the new joint and the body. There are many different kinds of material combinations used, such as ceramic on plastic, ceramic on ceramic, metal on plastic, and metal on metal. Materials used for joint replacements must be sturdy enough to withstand the various pressures and forces that may be applied to it. We will be looking at the design and manufacturing processes for joints as well as other important aspects to factor into the use of composites. Some important aspects to consider are the economic aspects and the market for joint replacements, and also the environmental aspects. We will also be discussing the future of joint replacements and the possibilities for increasing the success and longevity of the implants.
Joint replacement materials must pass a series of tests in order to meet their performance requirements. According to ISO 21535, hip replacement materials must be able to pass said series of tests, not limited to, but including a fatigue test, a range of motion test, and a high demand hip wear testing. For the fatigue test, there are two parts: the hip stem fatigue and the femoral neck fatigue part. For the hip stem fatigue part, the hip stem part of the replacement joint must meet the load requirement of 2,300 newtons. For the femoral neck fatigue part, the femoral neck part of the joint replacement must meet the load requirement of 5,340 newtons. For wear testing, which refers to ISO 14242-3, the implant must be cycled through the complex range of motion repeatedly to simulate what will occur once the implant is surgically inputted. And finally, for range of motion, the hip replacement should be made so that there is a full range of motion within this surgically inputted joint after 6 weeks of rehab.
Now to talk about the raw materials. In the 1960s and 70s, metal on metal was first to be used in hip replacements. The cobalt chromium was poorly manufactured and had little quality control, which led to an increase in use on metal on plastic. The metal on metal also caused impingements and wear on the surrounding bone. Now metal is more popular again due to controlled grain sizes and the smooth finish, and due to the fact that metal is stronger than polyethylene and tougher than ceramics. Metal on metal can also lead to toxicity poisoning, which is what led to the idea of replacing part of it with plastic. Metal on plastic is made from the same metals and polyethylene. Polyethylene is useful due to its high molecular weight and durability. It cannot be sterilized with gamma radiation while exposed in the air because the radiation breaks the chains and the broken ends will react with the oxygen present. This will decrease the molecular weight, ductility, and the strength of the polyethylene. This also leads to more wear, which means needing a new joint sooner. The parts are now sterilized in vacuum or with inner gases present instead of air. Radiation can also be avoided by treating polyethylene with ethylene oxide or gas plasma instead. It is better to use the altered radiation method because it increases the cross-linking, which will decrease wear down the line. Zirconia toughened alumina and polyethylene has less wear than metal on polyethylene. The ceramic is very hard, but it is brittle, which means it could fracture. They have been improving ceramics by increasing chemical purity and reducing the grain sizes. For ceramic on ceramic joints, the results are design dependent. Some reports for this material show no measurable wear and very few fractures. Some people have reported squeaking when in motion, but no other important side effects. Ceramics have a very limited use outside of hip replacements due to non-conforming surface shapes of other joints. It makes the parts very difficult to manufacture and control the quality of.
There are some advantages and disadvantages to using the gold standard method of a metal on plastic joint replacement. The advantages include being the least expensive, having the longest lifespan, and having the longest track record on safety. However, the disadvantages include the plastic may cause a breakdown of the bone, and this breakdown of the bone can lead to inflammation and other immune responses. However, there are some competing alternatives, such as ceramic on ceramic. It's the least likely to react with the body, but it can squeak when walking, shatter under heavy pressure, and lead to the necessary removal. There is also ceramic on plastic, which is best for people allergic to metal, but the plastic particles could lead to an immune reaction and inflammation. Finally, there is metal on metal, which is the longest lasting for young people, but potential toxins can lead to organ failure, damage, and death. So due to these facts, this method is almost never used.
Now to look at the design concepts for both hip and knee joint replacements. Both are made to be as seamless in the body as possible while also providing the range of motion similar to the original bone and cartilage. The hip replacement is made of a stem, a head, the liner, and the acetibular component or the cup. The stem part goes into the thigh bone and is typically made of titanium or cobalt chromium. The cup fits into the pelvis and is made from titanium as well. The head or ball is on the end of the stem and wedged into the cup. It is held in place by friction and is either a ceramic or metal. The liner is inside the cup and functions as a new cartilage. This is the part that will typically undergo wear and is made of ceramic, metal, or plastic depending on the kind of materials needed. The cup and liner are the parts that we looked at when discussing the material pairings. A knee replacement is also made of 4 parts. There is the femoral component on top and the tibial component on the bottom, which will hold the liner. There's also the liner in the middle that will serve as the new cartilage, which is made of polyethylene. Some doctors will also add in a new kneecap or patella. It is made of metal and the underside is covered in a piece of plastic to prevent metal on metal wear. If you look at the complex shape of the knee and implant, it can be seen why a ceramic implant would not be favorable. The shape is too complex for the quality of the implant to be better as a ceramic than a metal. Also, the ceramic would be too likely to fracture in a knee.
For the structure and manufacturing of joint replacements, specifically metal on plastic hip replacements, there are 2 parts to analyze: the plastic part and the metal part. For the plastic part, start by dissolving HDPE, which is a high-density polyethylene, which is also a thermoplastic polymer made from petroleum, and MWCNT, which is a carbon nanotube. And due to the planar honeycomb lattice of the carbon structure, MWCNTs are considered to be the ultimate high-strength fiber. So when mixing the MWCNT with the HDPE, the expectation is that the composite will be strengthened. This mix is then produced to form pellets, and then hot pressing occurs. Hot pressing is, of course, the process used for shaping fiber reinforced thermoplastics. The pellets are melted and then spread through the reinforcement to make the wanted shapes of the hip replacement. However, many times before the full part of the hip replacement is completed, the composite will go through tensile sample testing. Then the part is created and will go through the series of aforementioned tests. The Stryker titanium acetabular shell is the Stryker variation of the current gold standard hip replacement method. So overall, multi-axis and multitask machines are used for the component. So specifically for the metal part, which is the acetabular shell, this piece goes through the process of drilling, then interpolation milling, then finished off with a polishing insert. Once the entire manufacturing process is complete, the hip replacement is then produced to look much like the image on the left.
There are many economic aspects to factor into the cost of joint replacement surgery. Hip replacements are one of the most successful procedures done. Most of the implants can last longer than 15 years after the original surgery. Knee replacement implants generally last 15 to 20 years. Both of the amounts of surgeries are rising every year due to more injuries and diseases, and also the fact that many people have to get their implants redone eventually. The rate of increase for knee replacements is rising faster than the rate of increase for hip replacements. On average, the cost of a hip implant makes up about 21% of the total cost, and the cost of a knee implant makes up about 25% of the total cost of the surgery. The cost of implants ranges from $3,000 to $10,000. Another important factor for the economy is the loss of workers. The surgeries can take up to 4 weeks to recover from enough to go back to work. Even then, some people will not be able to return back to work due to pain or immobility. The potential market has been increasing over the past years due to a rise in aging population and a prevalence in chronic diseases. The growth of the market is also driven by technological advancements. Other key factors are people having more money, better medical facilities, and more accidents, which accelerates the rate of growth of the implant market. Other increases can come from easier access to knowledge of implants and initiatives by health insurance companies to support health issues. One of the main issues that lowers the market is the high cost for the treatment, but more research into cost-effective materials and manufacturing will hopefully lower the cost of implants.
In regard to the environment, joint replacements are not necessarily the best for the environment. On average, 5.2 kilograms of non-contaminated waste is produced during a joint replacement, and less than 1% of this waste is non-recyclable. So that waste breakdown looks like 57% of waste comes from paper pieces, 36% come from plastic pieces, 16% of this waste comes from cardboard, and less than 1% of the waste comes from metal. But even though less than 1% of the waste is non-recyclable, it all ends up going to the landfill. And so outflow to these landfills, as opposed to using the recycling trifecta, this has negative effects on the environment, but it also costs more money to send things to the landfill than it does to just recycle it from the beginning.
The future of joint replacements is based on the need to have longer-lasting implants and less wear on the body. Some researchers have proposed that changing the surface material in the joint can reduce the wear. Some tested materials have been diamond and hardened titanium, since both materials have a smooth exterior. These, however, would raise the cost of the implant, potentially by a lot. Most of the bulk materials used in the joint have not changed in the last 30 years. More research is being done to control grain sizes and minimize the defects present in order to better the implants. They may be more refined and controlled, but the base will most likely remain the same. Another possible development would be to try to decrease the amount of environmental waste. This will soon be important since the amount of people with implants has increased and they typically need to get new implants later in their lives. Some say that the next step for the joint replacements is to 3D print them, which allows for custom-made prostheses. This will allow for a better feel and function. It could improve the effectiveness of the surgery and reduce recovery times. The 3D printed joint can better fit to the bone, which allows for less bone to be cut, which leaves a larger surface area. This results in a stronger and better meld of bone to joint.
In conclusion, it has been discovered that the material and manufacturing of joint replacements, specifically hip replacements, are essential. 1 of every 12 adults above the age of 25 will need a joint replacement within their lifetime. And to add on to that, 44% of football players will need a joint replacement or already have one. And so given the price of these joint replacements, it is evident that there is a need for a long-term, comfortable solution that is also more environmentally friendly. So future designs should aim to optimize the size and lifespan of these replacements, while also increasing the resistance to wear and tear to create the best version of a joint replacement.
These are all the references we used. Thank you for watching.